point where the universe breaks somewhere in the silent dark between galaxies. A star trembles. For millions of years it has held itself together. A perfect equilibrium of gravity crushing inward and radiation pressing outward. But now, something deep within its heart has shifted. Atomic bonds begin to break. Pressure builds. A moment later, the star explodes with the force of a billion nuclear bombs, ripping apart its own body and scattering its atoms across the cosmos. That instant, the precise fraction of a second when balance collapses and chaos erupts, is known as a cosmic tipping point. It is the moment when the universe itself seems to crack. We tend to imagine the universe as eternal and steady. Stars shining, planets orbiting, galaxies drifting in calm, predictable harmony. Yet beneath that illusion of stability lies a delicate tension. Push anything, an atom, a planet, or even space-time itself, just slightly beyond a critical threshold and reality reshapes. Hydrogen fuses into helium. Matter implodes into neutronium. Space curves until time itself freezes. Everywhere we look, the cosmos is a tightrope act, and every so often it loses balance. In the coming hours of this investigation, we'll descend into that razor-thin boundary between order and collapse. We'll follow the thread from the surface of our own sun to the densest objects known to exist, neutron stars, those tiny remnants of once mighty suns that now spin like cosmic lighthouses across the void. They are the last step before complete destruction, the final checkpoint before a star becomes a black hole. But what lies inside them? That question has haunted astronomers for nearly a century. Neutron stars push matter to limits that physics can barely describe. Imagine a teaspoon of their material weighing more than the entire human population combined. Imagine mountains less than a millimeter high, because gravity there is so crushing that even the tallest peak would flatten instantly. Imagine dropping a pebble that would strike the surface at half the speed of light. And yet, somehow, these dead stars don't collapse. Something invisible holds them together. Something that, if understood, could rewrite the laws of nature. To grasp that mystery, we'll have to retrace a story that spans not just space but time. From the blazing experiments of our sun's core to forgotten wars, lost letters, and the improbable connections between poets, physicists, and soldiers. We'll meet a young Indian scholar expelled from school for political protest who would later discover how stars are built. A wounded British Marine whose injury in a World War I trench would lead to the birth of modern astrophysics. A scientist imprisoned in a Soviet gulag, whose son, working with Oppenheimer, would calculate the limit of existence itself. Their discoveries form a chain, each one revealing how matter behaves when pushed beyond its limits, each one inching us closer to the point where even physics starts to break. Inside a neutron star, everything we think we know, about atoms, forces, even the fabric of space, begins to unravel. The neat hierarchy of particles dissolves. Protons and electrons merge into neutrons. Neutrons may dissolve further into quarks. And deep in the heart, new, unknown forms of matter could emerge. Bose, Einstein condensates, hyperon soups, or even the long-sought fingerprints of dark matter itself. Every theory that tries to explain them faces the same question. How far can you push the universe before it breaks? Neutron stars are more than astronomical curiosities. They are laboratories for the fundamental laws of reality. They show us how gravity, quantum mechanics, and nuclear physics wage a silent war, and how one day, that conflict might reveal the next great revolution in science. Because when we stare into a neutron star, we are not just looking at the corpse of a sun. We are looking at a mirror, one that reflects the boundaries of our understanding. In this documentary, we'll journey from the first moments of stellar birth to the brink of cosmic collapse. We'll explore how ordinary atoms become extraordinary, how light bends, how time slows, and how the smallest particles decide the fate of entire galaxies. Along the way, we'll confront one uncomfortable possibility, that the laws of nature as we know them may only be temporary, approximations that crumble under the weight of a dying star. This is the story of the universe's most extreme survivors, of the stars that refuse to die quietly, of the hidden physics that keeps reality from tearing itself apart. And it begins not with an explosion but with a question: what truly happens at the point where the universe breaks? Part 1. The First Signs. A star on the edge. It is December 24th, 2024, Christmas Eve on Earth. While families gather under twinkling lights and snow drifts in silence, one machine built by human hands races through an inferno. The Parker Solar Probe, a car-sized spacecraft wrapped in a heat shield no thicker than a handful of coins, is hurtling around the sun at 200 kilometers per second, faster than any object we've ever made. At that speed, Parker could cross the continental United States in 15 seconds. Yet its destination is far more hostile. Just 6 million kilometers from the solar surface, deep inside the sun's outer atmosphere, a ghostly veil known as the corona. From Earth, the corona is visible only during a total solar eclipse, a radiant halo of white fire. But up close, it is chaos incarnate. A vast ocean of charged particles and magnetic fields whipping and curling with unimaginable force. It's here that the sun hurls enormous eruptions of plasma into space. Coronal mass ejections, each one a mountain-sized bomb of subatomic shrapnel that can rip through the solar system and slam into planets. If one such blast were to hit Earth directly, it could cripple power grids, shut down satellites, and plunge modern civilization into darkness. And yet, even at this distance, Parker's instruments are still struggling to explain why the corona burns millions of degrees hotter than the layers beneath it. Physics, it seems, is breaking its own rules right before our eyes. To understand this paradox, why a star's atmosphere is hotter than its surface, we must travel not through space, but back through time, more than a century before the Parker Solar Probe existed. The equation that named the stars Kolkata, India, 1905. The humid air presses like wet cloth against the city's colonial walls. Lord Curzon, the British viceroy, bends over a map, drawing lines that will divide Bengal along religious boundaries, a decision that will ignite protests across the region. Among the many young voices of dissent is a teenager named Meghnad Saha. Expelled from school for his part in the demonstrations, Saha's future seems broken before it begins. But exile turns into opportunity. Years later, now a professor, Saha will create one of the most powerful tools in astrophysics, the Saha ionization equation. With that single equation, astronomers can look at the light from a star, its temperature, its pressure, and calculate how much of its atoms are stripped of electrons. In other words, they can tell exactly what the star is made of. It's a revelation that rewrites our understanding of stellar physics. The same formula that explains the sun's faint outer glow also lays the groundwork for the physics of the deadliest objects in the universe, neutron stars. Ionization, Saha realized, is a kind of rebellion. When a gas grows hot enough, its atoms lose their electrons, transforming into a plasma, a churning, electrically charged soup that no longer behaves like ordinary matter. The hotter it becomes, the more chaotic its structure, until even atoms themselves surrender their integrity. It is, in many ways, a metaphor for the universe itself. Stability pushed past the point of no return. The heart of the sun descending from the corona through the chromosphere, temperatures drop briefly to around 5,000 degrees Celsius, before rising again as we reach the photosphere, the bright surface of the sun visible from Earth. Here, huge bubbles of plasma, each the size of continents, boil and churn, rising and falling in a slow, violent rhythm. But to glimpse what powers this titanic engine, we have to plunge deeper still. Beneath the roiling photosphere lies a zone of convective heat, then a dense radiative region where light itself takes 170,000 years to escape. At the center sits the core, a realm of crushing pressure and impossible density. In that heart, temperatures reach 15.7 million degrees Celsius, and each cubic centimeter contains 150 grams of matter, 8 times denser than gold. Every second, 620 million tons of hydrogen fuse into helium, releasing energy equivalent to 4 million tons of pure sunlight. This endless balancing act, the inward pull of gravity versus the outward push of nuclear fire, is known as hydrostatic equilibrium. It's the sun's most delicate dance. If gravity were to gain even a fraction of advantage, the core would collapse and ignite uncontrollable fusion. If the outward pressure won, the sun would tear itself apart. Yet for billions of years, it remains poised on that invisible line between life and death. Physicists express that balance through a simple formula, the equation of state, which ties together temperature, pressure, and density. A soft equation of state means matter is easily compressed. A hard one resists. The sun's equation of state has been mapped with astonishing precision, thanks to the most elusive particles known to science, neutrinos. Trillions of them pour from the sun every second, streaming through your body right now, through walls, oceans, and planets, barely interacting with anything at all. The number that pass through your thumbnail each second exceeds the number of humans who have ever lived. They are the ghosts of nuclear reactions, the messengers from the sun's core. And by measuring them, scientists have taken the sun's temperature from 150 million kilometers away. The result? 15.7 million degrees, stable for now. But stability in cosmic terms is only ever borrowed. The tightrope before collapse hydrostatic equilibrium cannot last forever. When the hydrogen runs out, the sun will falter. The heat that once countered gravity will fade. And when that happens, the equation of state, the very relationship that defines stability, will shift dramatically. Gravity will seize its moment. The sun will swell into a red giant, shedding its outer layers like a snake's skin, before collapsing into a white dwarf, the dense, smoldering core of its former self. But for stars much heavier than our sun, the end is far more violent. In them, gravity wins completely, crushing matter to the limits of physics, beyond atoms, beyond protons, until only neutrons remain. At that point, even the quantum laws that hold matter apart begin to strain. And when they break, a new kind of object is born. A neutron star, the universe's ultimate balancing act, teetering on the brink of collapse but never quite falling. For now, though, Parker's solar probe continues its orbit, a fragile human messenger skimming the edge of our own star's wrath. Its sensors hum, measuring electric fields, counting charged particles, reading the invisible tremors of magnetic storms. Every byte of data it sends home helps scientists refine the sun's equation of state, the very same principle that will one day determine the fate of dying stars. Because the forces that hold the sun steady are the same ones that decide when a star's heart gives way. And when it does, the light of creation turns into the darkness of collapse. Part 2. The Physics of Collapse. When stars turn against themselves in the grand clockwork of the universe, stars are its engines, vast nuclear furnaces that convert mass into light. Yet every machine, no matter how perfect, carries the seed of its own destruction. Inside each star, gravity and pressure are locked in a perpetual struggle. For billions of years, they balance each other like two hands frozen in an arm wrestle. But when the fuel that feeds fusion begins to run out, the balance tips. Gravity starts to win, and what follows is collapse. The final breath of a giant as a star exhausts its hydrogen. Fusion slows. The radiant pressure that once pushed outward begins to fade, and gravity, the ever-patient adversary, takes command. The core contracts, squeezing tighter and hotter, until helium itself begins to fuse. This new reaction provides only temporary respite. The process repeats with heavier and heavier elements, carbon, oxygen, silicon, each fusion stage shorter than the one before, until the star begins to manufacture iron. And that's where everything stops. Fusing iron does not release energy. It consumes it. The star has reached the end of its nuclear road. No amount of temperature or pressure can ignite the next reaction. Suddenly, there is no longer any force capable of holding gravity back. The star's inner layers plunge inward in free fall, slamming into the unyielding core. Within a fraction of a second, temperatures soar to billions of degrees. The rebound sends shock waves racing outward, tearing the star apart in a cataclysm so violent that it outshines entire galaxies. This is a supernova, the universe's most spectacular death cry. For a brief moment, matter ceases to behave as we know it. Atoms are shredded. Nuclei are smashed together to form exotic isotopes, scattering the heavy elements, gold, uranium, calcium, that will someday become planets, bones, and cities. But at the center of the chaos, something extraordinary happens. The core doesn't explode. It implodes. Gravity crushes it to such densities that the distinction between atoms, particles, and energy begins to blur. A teaspoon of that collapsed matter now weighs as much as Mount Everest. This is the birth of a neutron star. The quantum rebellion when the core collapses, protons and electrons are forced so close that they merge, creating neutrons and releasing neutrinos in an overwhelming flood. What remains is a sphere no larger than a city, about 20 kilometers across, containing more mass than our Sun. At these densities, the rules of ordinary matter no longer apply. It is as if the universe has crossed a boundary, a threshold where quantum mechanics and gravity are forced into direct confrontation. In the 1920s, a young English physicist named Ralph Fowler was among the first to realize what this meant. While recovering from a gunshot wound sustained at Gallipoli during World War I, Fowler began to study how electrons behave when packed tightly together. He discovered a strange quantum law known as the Pauli exclusion principle. No two particles can occupy the same quantum state. As a result, when matter is compressed beyond a certain point, its particles push back, not through heat or pressure, but through sheer quantum resistance. Fowler called this degeneracy pressure, and it was his insight that explained why white dwarfs, the remnants of smaller stars, do not collapse into oblivion. It is, in essence, the first safety net that keeps the cosmos from tearing itself apart. But there's a limit to how much degeneracy pressure can do. Fowler's student, the brilliant Indian astrophysicist Subramanian Chandrasekhar, calculated that a white dwarf cannot exceed 1.4 times the mass of our Sun before gravity overwhelms this quantum resistance. This threshold, the Chandrasekhar limit, marks the tipping point between white dwarfs and neutron stars. Beyond it, matter yields completely to gravitational collapse. The universe, it seems, is built on a hierarchy of resistance, each layer of matter surrendering to gravity in turn. When neutrons take over, neutron stars exist one level below this threshold, a new kind of equilibrium held together by the degeneracy pressure of neutrons themselves. These neutrons, each a tiny bundle of quarks, obey the same exclusion principle that protects white dwarfs. They resist being squeezed into the same state, creating an outward pressure that halts collapse, barely. The result is an object so dense that its gravitational pull bends light, time, and even space. Standing on a neutron star's surface, a pebble dropped from waist height would strike the ground at nearly half the speed of light. The tallest mountains would rise no more than a millimeter before their own weight flattened them. To an outside observer, the star appears to spin at impossible speed, hundreds of times per second, beaming radiation from its magnetic poles like a cosmic lighthouse. These pulses are so precise that some astronomers use them as natural atomic clocks, accurate to within billionths of a second. Yet even this new balance is precarious. Because somewhere inside these stars lies another frontier, a place where neutrons themselves may crumble into their constituent quarks. If that happens, the equation of state changes again, softening until gravity reclaims dominance. What happens next remains one of the deepest mysteries in astrophysics. The possible creation of a quark star, or perhaps the final collapse into a black hole, where even light cannot escape. The invisible test, the challenge for modern astronomy, is that we cannot see inside a neutron star. We can only infer its structure through the way it bends space, the radiation it emits, and the gravitational waves it generates when it collides with another of its kind. To decode these signals, scientists rely on models, thousands of possible equations of state, each describing how matter might behave under conditions that cannot be replicated on Earth. And every time a telescope captures a pulse, or a detector hears the faint ripple of a distant merger, we get one step closer to identifying which of those equations describes reality. The trouble is, each discovery seems to break the last model we built. In 2019, NASA's Neutron Star Interior Composition Explorer NICER, mounted on the International Space Station, detected a neutron star that shouldn't have existed, a behemoth twice the mass of the Sun, yet just as large as smaller stars. Its name, J0740 plus 6620. According to all known physics, a star that massive should have been crushed smaller. The size defied logic. Its very existence whispered that something fundamental, deep in the nature of matter, was missing from our equations. Was the core made of ordinary neutrons? Or was something else at work, perhaps dark matter, hyperons, or a Bose-Einstein condensate of subatomic particles moving in perfect unison? For the first time, scientists realized they might be staring at an entirely new kind of matter, something beyond the standard model, born only in the hearts of dying stars. In the ashes of stellar death, the universe is testing its own boundaries. From plasma to degenerate matter, from neutrons to quarks, every layer of collapse reveals a deeper rule and then breaks it. It's a cascade of tipping points, each more violent and uncertain than the last. The universe does not simply expand or contract. It negotiates with its own limits. And in that negotiation, neutron stars are its most radical experiments. Places where nature dares to ask, what if gravity never stops? Part 3: The Hidden Architects. The people who measured the edge of reality in the story of the universe. The collapse of a star is not just an astrophysical event. It's a human story, too. Behind every equation, every graph of pressure and density, lies someone who looked up at the night sky and asked, how far can nature go before it breaks? Some of those people never lived to see the consequences of their discoveries. Others changed physics without ever touching a telescope. And their paths, improbably, were shaped by war, exile, and chance encounters that would redirect the course of science itself. The Wounded Mathematician, March 1915. The Gallipoli Peninsula is a burning coastline. The air smells of salt and cordite, and the sea is choked with smoke from the wreckage of Allied battleships. Among the survivors pulled from the water is Lieutenant Ralph Fowler, a 26-year-old British Marine artillery officer. A bullet has torn through his shoulder. Fowler is sent home to recover, his military career abruptly ended. But the wound that takes him off the battlefield places him on another one, the battle for the soul of physics. Back in Cambridge, he meets a physiologist named Archibald Hill, who leads a small, eccentric group of scientists known as Hill's Brigands. Their mission: to apply mathematics to the chaos of war, to calculate artillery trajectories, sound waves, and explosive impacts with unheard-of precision. Fowler's quick mind and gift for abstraction make him invaluable. He learns to think in probabilities, to see patterns in destruction. When the war ends, he carries that perspective back to peacetime science. The universe, Fowler realizes, is not orderly. It is an arena of pressures and resistances, of balance and failure. The same laws that governed artillery shells can also describe the life and death of stars. He begins to apply quantum mechanics, a fledgling theory barely a decade old, to astrophysics, and in doing so, lays the groundwork for one of the most important insights of the 20th century: the structure of degenerate matter. The law of exclusion at the time, the inner workings of atoms, were a mystery even to experts. Physicists like Schrödinger, Heisenberg, and Bohr were inventing new mathematics to describe the strange rules of the subatomic world. One of those rules came from a young Austrian physicist named Wolfgang Pauli, who proposed that no two particles, specifically electrons, could share the same quantum state. This Pauli exclusion principle was puzzling at first, but Fowler saw its potential. If electrons resist sharing the same state, then in extremely dense environments like the core of a dying star, that resistance must create pressure. Not the ordinary pressure of heat, but a quantum mechanical one. He called it electron degeneracy pressure. In ordinary stars like the Sun, thermal pressure from fusion keeps gravity in check. But in dead stars where fusion has ceased, this new quantum pressure becomes the last defense against total collapse. It's as if the universe, unwilling to accept its own annihilation, has hidden an emergency brake inside the laws of physics. That discovery made Fowler one of the quiet architects of modern astrophysics. But as with all safety nets, his quantum brake could only hold so much weight. The student who broke the limit among Fowler's students was a 20-year-old Indian prodigy named Subramanian Chandrasekhar. In 1930, aboard a ship from India to England, The young physicist passed the long voyage doing calculations by hand, armed with little more than notebooks and stubborn curiosity. He wanted to know, what happens when a star's mass becomes too great for electron degeneracy pressure to resist gravity? Chandrasekhar combined the principles of quantum mechanics with Einstein's theory of relativity, an audacious move for someone barely out of his teens. The result was a precise numerical boundary, 1.4 times the mass of the Sun. That number would later be known as the Chandrasekhar limit, the invisible line between survival and collapse. Stars lighter than that limit end their lives as stable white dwarfs. Heavier stars cross the threshold and fall into deeper, stranger fates. Neutron stars or black holes. When Chandrasekhar presented his findings to the Royal Astronomical Society, his mentor Fowler applauded. But not everyone did. Arthur Eddington, the celebrated British astronomer who had famously confirmed Einstein's general relativity by measuring the bending of starlight, stood up and publicly challenged the young scientist. Eddington couldn't accept that nature would allow such absurd objects to exist, stars that could collapse into points of infinite density. The star, he insisted, must somehow find a way to stop. It was, ironically, a statement that revealed more about the limits of human imagination than about the universe itself. Chandrasekhar, humiliated but undeterred, continued refining his theory. He would later win the Nobel Prize for it, though not until half a century later. By then, telescopes had proven him right 1,000 times over. The legacy of Fowler and Chandrasekhar. Fowler died in 1944, never receiving the Nobel recognition he deserved. But his ideas, carried forward by Chandrasekhar, had redrawn the boundary between matter and collapse. They showed that the universe has a hierarchy of resistance. Thermal pressure keeps living stars stable. Electron degeneracy stabilizes white dwarfs. Neutron degeneracy stabilizes neutron stars. And beyond that, perhaps, lies nothing but the event horizon of a black hole. Each level represents a new equation of state, a deeper layer in the cosmic onion of matter. And each level carries its own tipping point, a moment where the rules fail and something unprecedented emerges. In that sense, Fowler and Chandrasekhar weren't just studying stars. They were mapping the boundaries of existence itself. The universe's secret ladder to grasp what they uncovered. Imagine compressing the Earth into a marble, the marble into a grain of sand, the grain into a speck smaller than an atom, each step taking you closer to a neutron star. At every stage, some new physical law pushes back. Heat, electromagnetism, quantum exclusion. But once you breach the Chandrasekhar limit, those defenses collapse. The ladder ends. Or does it? Decades later, physicists would realize that even neutrons, once thought indivisible, are made of smaller components called quarks. Inside neutron stars, pressures may grow so intense that neutrons dissolve into a soup of quarks and gluons, a form of matter last seen in the first microsecond after the Big Bang. If that's true, then these collapsed stars are not just remnants of stellar death. They are time machines, holding inside them the conditions of the infant universe. For the scientists who study them, Fowler and Chandrasekhar's equations were not the end of the story but the beginning of a deeper question. How many times can matter reinvent itself before it ceases to exist? A universe built by the wounded and the exiled. It is one of history's great ironies that the people who defined the limits of the cosmos often learned about limits the hard way. Saha, expelled from school. Fowler, wounded in war. Chandrasekhar, ridiculed by his hero. Yet from those fractures came understanding. They revealed that the same physics governing the fall of empires and the death of stars springs from the same truth. Pressure creates transformation. And in that transformation, the universe finds a way to survive its own collapse. The men who mapped these invisible thresholds never lived to see the neutron stars that would prove them right. But the equations they left behind became the skeleton of the cosmos, a mathematical architecture that explains not only why stars die, but why they don't disappear completely. Because somewhere between light and darkness, there is a narrow space where reality still holds, a place where the laws of quantum mechanics whisper, not yet. And that whisper is the sound of the universe, refusing to break. Part 4. The Eye of the Explosion. From the Dog Star to the Crab Nebula on a clear winter night in the northern hemisphere, one star outshines them all. Low on the horizon, shimmering through the frosty air, it burns with a brilliance that flickers blue, white, and crimson, as though the entire spectrum of light has been trapped inside a single point. This is Sirius, the Dog Star, brightest in Earth's sky and one of the oldest companions of human mythology. To ancient Egyptians, Sirius heralded the flooding of the Nile, the promise of renewal. To the Romans, it marked the dog days of summer, when its rising alongside the sun signaled heat and hardship. But to modern astronomers, Sirius hides a secret far stranger than myth, because this radiant star is not alone. The pup beside the giant orbiting Sirius is an invisible companion, so faint it eluded detection until the 19th century. Astronomers noticed that Sirius wobbled slightly, as if tugged by a hidden partner. When that companion finally revealed itself, the revelation was staggering. It was smaller than Earth, yet burned hotter than the sun. They called it Sirius B or simply the pup. At first, the pup defied understanding. How could something so tiny shine so fiercely? How could a star, stripped of its outer layers, remain so dense? Its existence was proof of something entirely new, a state of matter unlike anything seen on Earth. This was the first white dwarf ever observed, the bare, collapsed core of a once massive star. For decades, white dwarfs remained the strangest objects in the known universe. Stellar corpses that refused to fade, still glowing faintly with the leftover heat of nuclear fire. But as physicists like Fowler and Chandrasekhar refined their theories, it became clear that white dwarfs were not the end of the story. They were a doorway, the first rung on the ladder to something even more extreme. The weight of light. To understand just how bizarre white dwarfs are, imagine crushing an entire sun into a sphere no larger than our planet. Each cubic meter of that material would weigh 1 billion kilograms. A sugar cube of white dwarf matter would weigh as much as an elephant. A shipping container full would rival the Great Pyramid of Giza. And yet, the star does not collapse. Its structure is held aloft by electron degeneracy pressure, the quantum repulsion Fowler had described years earlier. In this bizarre realm, the atoms themselves have dissolved, stripped of electrons and packed so tightly that the Pauli exclusion principle alone keeps them apart. It's the most literal expression of resistance in nature, the universe's refusal to occupy the same space twice. But even this resistance has a breaking point. If gravity grows stronger, if the star's mass crosses Chandrasekhar's threshold, the electrons will be forced into the protons, collapsing the matter even further. At that moment, the electrons disappear. The protons merge. What remains are neutrons, and the white dwarf becomes something far denser, far darker, a neutron star. The guest star of 1054. To find evidence of such a transformation, astronomers had to look not at the gentle glow of Sirius but at the violent aftermath of stellar death. One of the best clues lies in the Crab Nebula, a tangle of multicolored gas and dust located in the constellation Taurus. In the year 1054, Chinese astronomers recorded the sudden appearance of a guest star in that same patch of sky. It was so bright it could be seen in daylight for nearly a month, and at night for almost 2 years. What they had witnessed was a supernova, the explosive death of a massive star. The debris of that explosion still drifts through space today, captured in intricate filaments of glowing gas. And at its center lies something extraordinary. A tiny, rapidly spinning neutron star, just 21 kilometers wide, smaller than London, narrower than Tokyo, yet containing more mass than our entire sun. It is the heart of the Crab Nebula, a cosmic lighthouse pulsing 30 times per second, sweeping beams of radiation across the universe. Each pulse is the cry of a star that should no longer exist. The smoothest mountains in the universe. To grasp how extreme this object is, consider gravity. On Earth, a rocket must reach 11 kilometers per second to escape. On a neutron star, the escape velocity is 150,000 kilometers per second, half the speed of light. Under such gravity, no mountain could stand higher than a fraction of a millimeter. The entire surface is nearly featureless, smoother than polished glass. Yet beneath that smoothness lies chaos. Atomic nuclei crushed so tightly that their electrons have merged, leaving a sea of neutrons swimming in superfluid motion. This, then, is what happens when matter is pushed past its final limit. White dwarfs are the end of small stars. Neutron stars are the remnants of giants. But what holds them together is even more mysterious than the degeneracy pressure of electrons. Within a neutron star, neutrons themselves, neutral, unyielding, indivisible, are packed to such extremes that they too begin to resist. Their resistance creates a new form of degeneracy pressure, the final safety net before gravity wins forever. Chandrasekhar's calculations had shown that electron degeneracy pressure fails at 1.4 solar masses. Later work by Tolman, Oppenheimer, and Volkoff would show that neutron degeneracy can hold only up to about 2.2 to 2.9 solar masses. Beyond that, not even quantum mechanics can save the star from its fate. Past that limit, collapse becomes unstoppable. And when it does, the universe gives birth to something even more terrifying: a black hole. A universe of pulses, the discovery of pulsars, rapidly rotating neutron stars, in 1967 by Jocelyn Bell Burnell, offered humanity its first tangible proof of the strange new world. At first, the rhythmic radio signals puzzled astronomers. The pulses were so regular they seemed artificial. Some even speculated, half-jokingly, that they might be messages from aliens, labeling the first detection LGM-1 for little green men. But soon it became clear, these were not beacons of life, but of death. They were the dying spins of collapsed stars, their magnetic fields whipping space like cosmic turbines. Today, thousands of pulsars have been catalogued. Their precision rivals that of atomic clocks. Their timing is so stable that physicists use them to test general relativity, to measure gravitational waves, even to map the structure of spacetime itself. Each pulse that reaches Earth is a reminder, a beat of the universe's hidden rhythm, echoing from a star that crossed the line between existence and oblivion. The light that outlasts death, the Crab Nebula pulsar, continues to spin, sending radio waves and X-rays through space nearly a millennium after its parent star's explosion. It is, in a sense, a ghost engine, a dead star that refuses to die completely. Its rotation gradually slows as it loses energy, but even that deceleration provides valuable data. By measuring how fast it fades, astronomers can infer the star's magnetic field strength, its mass, and even the composition of its interior, a clue to the elusive equation of state that defines all neutron stars. And that equation, in turn, holds the key to one of the greatest puzzles in modern physics. How does matter behave when crushed to densities beyond the reach of experiment? Because somewhere beneath that smooth surface, beyond the crust and into the core, something extraordinary may be happening. Something that forces us to rethink what the word matter even means. The night sky above us is littered with the ashes of long-dead stars, but a few, like the Crab pulsar, still whisper from the darkness. Each pulse is a heartbeat of the cosmos, proof that even destruction can give rise to order. In every dying star, the universe seems to ask the same question: can the laws that built me also unmake me? Part 5, Into the Core. The anatomy of a neutron star. Picture an astronaut, tethered to the hull of the International Space Station. Earth spins silently below, a swirl of white clouds and deep ocean blue. Around her, the void is absolute. No sound, no air, no horizon. She checks her instruments, adjusts her grip, and drifts toward a piece of equipment no larger than a washing machine bolted to the station's frame. It's called NICER, the Neutron Star Interior Composition Explorer. And it is, quite literally, humanity's eye into the densest places in the universe. The telescope that listens to dead stars. NICER doesn't look like a conventional telescope. Instead of mirrors or glass lenses, it carries a collection of gold-lined cylinders, X-ray concentrators, each one designed to catch high-energy light invisible to human eyes. Its mission: to measure the flickering radiation coming from distant neutron stars. For these remnants of stellar collapse, light doesn't stream smoothly. It pulses, spins, and vibrates, carrying subtle clues about what's happening deep inside. Every flicker is a fingerprint of pressure, temperature, and density, the ingredients of the equation of state that defines a neutron star's structure. In May 2023, a small micrometeoroid punched a hole through NICER's protective shielding. A tear no larger than a postage stamp, but enough to let stray sunlight flood its sensors. The damage was catastrophic. The telescope's readings blurred and distorted. For months, engineers debated whether it could be repaired. Then, in January 2025, an audacious spacewalk changed everything. 2 astronauts, wearing suits rated for extreme thermal swings, performed what NASA called surgery in orbit. Working in zero gravity with gloves thick as armor, they patched the damaged foil layers one by one. By the time the sun rose over the Pacific, NICER was alive again, ready to peer once more into the hearts of dead stars. The thinnest atmosphere in the universe, the data NICER sends back is unlike anything ever seen. Each neutron star it observes appears to be wrapped in a film of hydrogen and helium no thicker than 10 centimeters. An atmosphere with the density of diamond and a temperature exceeding 2 million degrees Celsius. Beneath that blazing film lies a crust of unimaginable rigidity. The pressure is so intense that electrons are stripped from their nuclei, leaving a sea of positively charged ions suspended in a haze of freed electrons. Deeper still, those ions begin to deform under stress. Protons and neutrons twist into long, thin filaments, structures that, in a whimsical stroke of human imagination, physicists have named nuclear pasta. They're not being poetic. The shapes really do resemble food. In the upper crust, the particles cluster into spheres like gnocchi. Further down, they stretch into spaghetti, and finally flatten into sheets like lasagna. It's absurd and beautiful, a cosmic kitchen built from atomic nuclei. Computer simulations suggest that this nuclear pasta might be the strongest material in the universe, 10 billion times tougher than steel. It's the scaffolding that prevents a neutron star's outer layers from collapsing inward, the last barrier before the matter inside crosses into even stranger states. And yet, all of this, the crust, the pasta, the atmosphere, is no more than a skin. It measures just 100 meters thick, yet it weighs more than 3,000 Earths. Beneath it lies the unknown. The star that shouldn't exist in 2019, NICER focused on a neutron star catalogued as J0740 plus 6620. It quickly became one of the most puzzling objects ever measured. J0740 is massive, over twice the mass of our Sun. Yet somehow it's the same size as other neutron stars, half its mass. By all known physics, it shouldn't be possible. The more massive a star becomes, the stronger its gravity should be, and the more tightly it should be crushed. The rule is simple. Heavier means smaller. But J0740 refused to obey. Its radius was too large, its density too low. Something inside was resisting compression, something beyond the standard models of neutron matter. The data threw astrophysicists into turmoil. Had they been using the wrong equation of state all along? For decades, researchers had built hundreds of such equations, each one describing how matter behaves under extreme pressure. But no laboratory on Earth can reproduce the conditions of a neutron star's core, trillions of times denser than lead, with magnetic fields 100 billion times stronger than anything humans can create. If J0740 was real, and every observation confirmed that it was, then the universe itself was signaling that our understanding of matter was incomplete. What lies beneath the pasta to explain J0740? Scientists proposed a radical new possibility. Perhaps the star's interior wasn't just neutrons. Maybe, deep beneath the crust, the neutrons had begun to unravel into their smaller constituents, the quarks that make them up. Ordinary matter is made from just 2 kinds of quark, up and down. But under the crushing gravity of a neutron star, strange things happen. Literally strange, because one of the next families of quarks is called the strange quark. If the pressure and temperature in the core are high enough, neutrons could break apart into a fluid of unbound quarks, a quark-gluon plasma, where particles move freely, no longer confined within nuclei. It would be a microscopic ocean of primordial matter, identical to what filled the universe less than a millionth of a second after the Big Bang. But that theory comes with a problem. Freeing quarks costs energy. And the energy needed to tear them apart should make the star more compressible, not less. In other words, a quark core should make a neutron star smaller, not larger. J0740, stubbornly inflated, seemed to contradict that entirely. The strange and the dark to solve the paradox, astrophysicists turned to even more exotic possibilities. Perhaps the interior of J0740 contains particles beyond the standard model. Hyperons, built not just from up and down quarks, but from strange ones as well. These particles, heavier than neutrons, could exist stably only under immense pressure. Yet even that explanation falls short. The presence of hyperons would soften the equation of state, making the star more squishy, not less. J0740, by contrast, appears to be unusually rigid. Then another hypothesis emerged, one that felt almost poetic in its symmetry. What if neutron stars don't just compress ordinary matter, but collect dark matter as well? As massive stars drift through the galaxy, they plow through clouds of invisible dark matter, gravitationally capturing tiny amounts over millions of years. When they collapse into neutron stars, that dark matter remains trapped at the core, interacting only through gravity. Adding even a small fraction of dark matter to the mix could harden the equation of state, creating extra resistance against compression. In that case, J0740's strange size might be not a contradiction, but a clue. If true, neutron stars may be the first objects in the universe to reveal what dark matter truly is. The new frontier, what NICER began in 2019, has since reshaped the entire field of high-energy astrophysics. Each neutron star observed, each flicker measured, eliminates a dozen theoretical models. The data narrows the possibilities, and with them the number of viable theories for the fundamental laws of physics. In the dense hearts of these dead suns, quantum mechanics, nuclear physics, and general relativity all collide. And for the first time we can watch that collision unfold, not in equations but in light. The search for the true equation of state is no longer just about stars. It's about understanding where the universe itself starts to fracture, the point where all known theories begin to fail. Because inside a neutron star, matter is pushed to the breaking point, and what happens next may tell us not only how stars die, but why the universe exists at all. Part 6. The Impossible Core. Quarks, hyperons, and the search for the ultimate matter at the deepest level of the neutron star, far below the crust of nuclear pasta and the dense mantle of neutrons, lies a place where theory begins to tremble. It is a region we cannot see, cannot recreate, and cannot yet fully describe. A place so extreme that even the language of physics struggles to hold its shape. Here, the pressures are trillions of times greater than anything achievable on Earth. Here, atomic nuclei no longer exist. Here, the fundamental building blocks of matter begin to come undone. This is the impossible core, the point where our theories of nature meet their own event horizon. Breaking the neutron to understand what might dwell inside this forbidden center, we have to strip matter down to its essence. A neutron, the neutral particle that gives neutron stars their name, is itself not fundamental. It is made of three smaller particles called quarks, two down quarks and one up quark, bound together by the strong nuclear force. This force, carried by particles known as gluons, is the mightiest in nature, a cosmic rubber band so strong that quarks can never be separated under normal conditions. But inside a neutron star, nothing is normal. The weight pressing inward is so vast that it may stretch this subatomic rubber band to its breaking point. When that happens, the quarks escape confinement, creating a fluid of free-moving quarks and gluons, a quark-gluon plasma. Physicists have produced this state fleetingly in particle colliders on Earth, like CERN's Large Hadron Collider and Brookhaven's RHIC. But even those monumental machines achieve such conditions for less than a trillionth of a second. A neutron star's core, on the other hand, may sustain them for millions, even billions, of years. If true, then every neutron star is not only a stellar corpse, but a living relic of the Big Bang, preserving within it the same exotic matter that filled the universe when it was less than a microsecond old. The quark soup hypothesis, the idea that neutron stars might hide a core of free quarks, often called a quark soup, is both elegant and unsettling. In this model, the outer layers remain ordinary neutron matter, while the core transitions smoothly into quark matter. This inner region would behave like a superfluid, its particles flowing without friction, possibly creating vast magnetic vortices that ripple outward through the star's crust. Such a structure could explain certain astronomical observations, like the sudden, tiny changes in a pulsar's spin rate, known as glitches. If the crust floats atop a quark core that behaves like a fluid, then occasional shifts between the two layers could send shockwaves racing across the star's surface, altering its rotation. But even here, the math doesn't quite fit. Freeing quarks from their bonds requires energy, and that energy has to come from somewhere, the star's gravitational well. That means a quark core should make the star softer, more compressible, not harder. Yet the nicer data from J0740 plus 6620 shows the opposite. Something inside the star is resisting collapse more than predicted. The quark soup theory, once the leading candidate, suddenly looks incomplete. The strange ones in the 1960s, particle physicists discovered an entire zoo of new particles, including some that contained a third type of quark, the strange quark. These strange particles are heavier and rarer than the up and down quarks that make up ordinary matter. On Earth, they decay almost instantly, but inside a neutron star under such extraordinary pressure, they might persist. A neutron that converts one of its down quarks into a strange quark becomes a hyperon, a particle that doesn't exist naturally anywhere else in the cosmos. If enough hyperons form, they could dominate the star's core, producing what physicists call strange matter, an exotic blend of ordinary and strange quarks bound together by the strong force. In theory, strange matter could be so stable that if a droplet of it touched normal matter, it would convert everything it encountered into more strange matter, spreading like an infection through the universe. These hypothetical fragments, called strangelets, would be the ultimate contagion capable of transforming stars, planets, even living tissue into quark paste. Fortunately, no evidence of such a disaster has ever been found. But the math is both fascinating and terrifying. If hyperons really do exist in the cores of neutron stars, their presence should soften the equation of state. That would mean fewer heavy neutron stars could survive before collapsing into black holes. And yet, once again, J0740 breaks the rule. Its size and density imply a core that's harder, not softer. The strange matter hypothesis, too, begins to wobble. The Bose-Einstein conjecture: when all known possibilities fail, physicists look to the unknown. And sometimes, the answers lie not in smashing particles apart, but in how they come together. In the 1920s, Indian physicist Satyendranath Bose, working with Albert Einstein, discovered that some particles, called bosons, could occupy the same quantum state. Unlike fermions, such as protons, neutrons, and electrons, which obey the exclusion principle, bosons can overlap perfectly. Under the right conditions, they merge into a single collective quantum entity, a Bose-Einstein condensate BEC. On Earth, BECs are created at near absolute zero, when atoms move so slowly that their wave functions fuse into one. But inside a neutron star, something similar could happen for entirely different reasons. If pairs of neutrons or even pairs of quarks align their spins, they could behave as composite bosons. And if they do, they could form a Bose-Einstein condensate at incredibly high temperatures, creating a new superrigid form of matter. This would harden the equation of state dramatically, precisely what we observe in J0740. If true, then the most massive neutron stars might not be neutron stars at all. They could be Bose-Einstein condensate stars, objects made of a single quantum wave of matter, unified and stable in ways we barely understand. Inside them, the line between particle and field disappears. The star becomes one vast quantum object, spinning and glowing like a solidified fragment of the universe's wave function. When darkness hardens light, even more speculative, yet increasingly plausible, is the idea that dark matter contributes to the stiffness of a neutron star's core. Dark matter doesn't interact electromagnetically. It passes through ordinary matter almost freely, but gravity affects it all the same. Over millions of years, massive stars would collect dark matter as they orbit through the galaxy. When those stars die, the captured dark matter remains trapped in the collapsed core. Unlike neutrons or quarks, dark matter particles might not compress easily. Even a small concentration could drastically alter how the star resists gravity. In simulations, adding dark matter to the core indeed reproduces a harder equation of state, enough to explain J0740's strange size without invoking new forces or particle types. It's an elegant solution, though far from proven. If verified, it would mean that neutron stars are not just laboratories for quantum physics. They are dark matter detectors, hidden in plain sight, waiting for us to decode their message. The core that rewrites physics, whichever theory proves correct: quark soup, strange matter, condensate, or dark matter hybrid. The conclusion is inescapable. Neutron stars are more than stellar remnants. They are the testing grounds for the next revolution in physics. In their cores, matter is squeezed to densities that mock our equations. Here, gravity and quantum mechanics, two theories that have never truly agreed, are forced to share the same stage. And somewhere in that impossible core lies the key to uniting them. Perhaps the universe built neutron stars as its own experiments, to explore what happens when nature approaches its breaking point. If we can decode them, we won't just understand stars. We might finally understand everything. Part 7: The TOV Limit. How heavy can a star become before it disappears? Every structure in the universe, from mountains to galaxies, exists because something resists collapse. But resistance has limits. A bridge can bear only so much weight before it buckles. A planet can hold only so much mass before it ignites into a star. And a neutron star, the densest known object short of a black hole, can carry only so much gravity before even quantum mechanics yields to the void. That final threshold has a name whispered with awe in astrophysics: the Tolman-Oppenheimer-Volkoff limit, or TOV limit. It is the ultimate weight limit of matter, the point at which the universe itself says no more. The architects of the limit. The story begins in 1938, in the quiet offices of Princeton University. Einstein was there, pacing through his final years of work. But down the hall, two young physicists, Robert Oppenheimer and George Volkoff, were building a different kind of theory. Guided by the earlier work of Richard C. Tolman, they combined the principles of general relativity with the equations of hydrostatic equilibrium, the mathematical balance between pressure and gravity that determines a star's structure. Their goal was simple yet profound: to calculate what would happen if a star's mass exceeded the ability of neutron degeneracy pressure to resist collapse. The result of their work, the TOV equation, became the backbone of neutron star physics. It showed that as a star grows heavier, gravity steepens spacetime so drastically that even the strongest pressure cannot counteract it. In other words, there's a tipping point beyond which the star cannot exist as matter. It must collapse into a black hole. At the time, this was a purely theoretical prediction. Neutron stars themselves had not yet been observed. But Oppenheimer and Volkoff estimated the limit to be roughly 0.7 solar masses, a value later refined upward as better nuclear models emerged. Today, the TOV limit is believed to lie between 2.1 and 2.9 solar masses. The exact number remains unknown, and that uncertainty hides the boundary between two worlds. The star that crosses the line when a neutron star's mass approaches the TOV limit, its behavior becomes erratic. The slightest increase, a few hundredths of a solar mass, can trigger runaway collapse. If the star accretes material from a companion or merges with another neutron star, it risks crossing that invisible line. In an instant, the balance shatters. The pressure that once held it aloft can no longer resist gravity's pull. No explosion follows, no bright flash, no supernova. The collapse is silent. The star simply vanishes, swallowed by its own warping of spacetime. The transition from neutron star to black hole is not gradual. It is a phase change of existence, the final failure of matter to remain matter. The TOV limit is therefore more than a number. It is a philosophical threshold, the border between the physical and the unknowable, between what can be seen and what can only be inferred. The messenger from the deep for decades, the TOV limit was a theoretical curiosity. Then, in August 2017, the universe spoke. On the 17th of that month, observatories around the world, and for the first time gravitational wave detectors, captured a signal unlike any before it. Came not as light, but as a ripple in spacetime itself. The event was catalogued as GW170817, a gravitational wave generated by the merger of two neutron stars, roughly 130 million light-years away in the galaxy NGC 4993. The collision unleashed a torrent of data: gamma rays, X-rays, visible light, and gravitational waves. For the first time, scientists could watch two neutron stars spiral together and collide, and see what remained afterward. The initial impact created a single, massive neutron star, one far heavier than any previously observed. But within seconds, its signal faded. The object had collapsed into a black hole. The message was clear. The newly formed remnant had crossed the TOV limit, and nature had enforced its law. From that event alone, astrophysicists could set an upper bound on the mass of stable neutron stars, about 2.17 solar masses. Everything heavier must collapse. Everything lighter can survive. It was the first empirical measurement of the universe's ultimate weight limit. The tightrope between existence and oblivion, the TOV limit, isn't a sharp line. It's a tightrope. A neutron star that weighs 2.0 solar masses can persist for billions of years. But add just a fraction more, the equivalent of Earth or Jupiter, and the star tips over the edge. It's an exquisite balance, like standing on the knife's edge of space-time. This is why so many neutron stars exist in binary systems, locked in dangerous relationships with their companion stars. They siphon matter slowly, growing heavier, inching toward the TOV threshold. Some manage to hover just below it, spinning faster and faster to stay stable. These are the millisecond pulsars, whirling hundreds of times per second, cosmic figure skaters conserving angular momentum to avoid collapse. But the moment they lose that spin, or accrete just a bit too much, gravity wins. The star folds inward. Its magnetic field, once stretching thousands of kilometers, snaps shut like a trap. And in less than a heartbeat, all light, all structure, all time itself vanish into the dark. What the limit reveals, the TOV limit, may appear to be about stars, but it is also a test of the laws of physics. Every equation of state, every model of how matter behaves at extreme densities, predicts a slightly different limit. If astronomers can measure that number precisely, they can rule out entire branches of nuclear theory. A limit closer to 2.0 solar masses would suggest that exotic particles like hyperons soften the core. A limit near 3.0 would hint that new forms of matter, perhaps quark condensates or dark matter admixtures, are stiffening the equation of state. Thus, the TOV limit isn't just an upper bound. It's a diagnostic of reality itself. It tells us what kinds of particles exist, how strong the nuclear forces truly are, and where quantum mechanics stops obeying itself. In that sense, measuring the TOV limit is like probing the seam between two universes, one of light, one of gravity. The physics of failure, even the way a neutron star fails to exist, reveals deep truths about the cosmos. When a star crosses the TOV limit and collapses into a black hole, the energy released in gravitational waves rivals that of the visible universe. Yet it happens in perfect silence. Matter doesn't explode. It disappears. The event horizon forms before light has time to escape. In that final moment, all distinctions vanish. Protons, neutrons, quarks, even space and time themselves. The universe, confronted with its own impossibility, simply hides it. This is why the TOV limit holds such symbolic power. It is the point at which the knowable world ends. Every telescope, every detector, every equation, all of them are, in a sense, instruments designed to stare at that line and ask what happens next. The limit that moves, but the story doesn't end there. Recent simulations suggest that the TOV limit might not be a fixed number after all. Under certain conditions, like rapid rotation or extreme magnetic fields, a neutron star can exceed the traditional limit, at least temporarily. These supermassive neutron stars can exist for a few seconds, minutes, or even years, held up by centrifugal force or magnetic pressure. Eventually, though, friction and radiation slow them down. And when they do, the star crosses the threshold and collapses. This delayed collapse may explain a strange cosmic phenomenon. Short gamma-ray bursts, brief flashes of high-energy light lasting less than 2 seconds. Many astronomers now believe these bursts are the dying screams of supermassive neutron stars finally succumbing to gravity. The TOV limit, it seems, is not just a number. It's a moving frontier, one that shifts with time, rotation, and magnetic fury. The universal weight of being, if there's a poetic truth to be drawn from the TOV limit, it is this: everything in the universe has a breaking point. Even light, even space, even the stars that built us. The same physics that holds a neutron star together holds us together, too. We are made of the debris of those very collapses, atoms forged in the brief reprieve between pressure and gravity. When we study the limit of a dying star, we are really studying the limits of ourselves, how far order can persist before the void reclaims it. And somewhere, out there in the dark, another star spins at the edge of its existence, defying collapse for one more heartbeat. For now. Part 8. The collision. When neutron stars merge and space itself rings for most of their lives, neutron stars are solitary, silent remnants of long-dead suns, spinning endlessly in the dark. But sometimes, two of them are born together. They circle each other for billions of years, locked in a fatal waltz. Each orbit tightens the spiral, each revolution draws them closer, until one day, they meet, and the universe itself rings. The slow spiral of doom. Imagine two neutron stars orbiting one another, each about 20 kilometers wide yet heavier than our sun. At first, they are separated by a few 100,000 kilometers, the distance between Earth and the Moon. But over time, they emit gravitational waves, ripples in the fabric of spacetime predicted by Einstein a century ago. These waves carry away energy, causing the stars to spiral inward. Their dance quickens. Every orbit accelerates their rotation. Every heartbeat of gravity brings them closer. In the final minutes, their speed approaches a third the speed of light. The gravitational field between them grows so strong that space itself stretches and compresses in rhythm. If your body could survive such a place, you would feel the universe breathe. Then, in one blinding instant, they collide. The kilonova, the impact is beyond comprehension. Each star releases a burst of energy equivalent to the detonation of 10 to the power of 46 nuclear bombs. Temperatures soar to billions of degrees, and matter, compressed beyond atomic structure, is violently ejected into space. This cataclysm is called a kilonova, a transient explosion roughly 1,000 times brighter than a classical nova. It lasts for days, sometimes weeks, and it forges the rarest elements in the universe: gold, platinum, uranium, every atom of these heavy metals on Earth, the gold in our jewelry, the platinum in our electronics, the uranium buried deep in ancient rock, was born in the merging hearts of neutron stars. It's a staggering truth. The ring on your finger was once part of a dying sun. The symphony of spacetime, when the first kilonova was detected on August 17, 2017, it changed astrophysics forever. Two detectors, LIGO in the United States and Virgo in Italy, captured a faint, oscillating signal, a chirp that lasted just over 100 seconds. That chirp was the sound of two neutron stars colliding, the first gravitational wave event ever linked to visible light. Just seconds later, space telescopes across the globe turned their eyes to the same patch of sky. In a small galaxy called NGC 4993, astronomers saw a new point of light flaring into existence, the optical afterglow of the merger. It was the first time humanity had both heard and seen a cosmic event. Physics had become multisensory. For the next several days, the light from the kilonova changed color, from bright blue to deep red, as the heavy elements it forged cooled and expanded. From that color shift, scientists could calculate exactly what was being made. Within hours, they confirmed the production of our process elements, the heaviest atoms known to exist. In that single explosion, the universe had minted 10 Earth masses of gold and 5 of platinum. The last breath before the black hole at the heart of the explosion, the merged neutron stars briefly form a single, hypermassive object. A star too heavy to exist, spinning too fast to die. For a few seconds, it resists gravity through sheer momentum and magnetic fury. Its rotation winds magnetic field lines into colossal spirals, generating jets of plasma that shoot out from its poles at nearly the speed of light. These jets pierce the surrounding debris, producing a short gamma-ray burst, one of the brightest phenomena in the universe. Then, inevitably, the rotation slows, the magnetic field collapses, and the star, now above the TOV limit, falls inward. A black hole is born. Even in death, the event continues to radiate for eons, its aftermath glowing in X-rays and radio waves, slowly fading as the expanding cloud of heavy elements disperses into interstellar space. In time, those atoms will seed new worlds, new suns, perhaps even new life. The death of 2 stars becomes the genesis of countless others. The echoes of the universe's gravitational waves are unlike any other form of observation. Light can be absorbed or deflected, but gravity passes through everything. Even through you right now, stretching and compressing your atoms by less than a proton's width as distant stars collide. These ripples carry pure information about motion and mass. They reveal not just what happened, but how space itself responded. By studying their patterns, physicists can reconstruct the final moments of neutron-star mergers, their masses, their spins, even the properties of matter at their cores. Each gravitational wave is a cosmic fingerprint, carrying the secrets of the universe's most extreme environments. The 2017 merger wasn't just a discovery. It was a beginning. Since then, detectors have captured dozens more, each one sharpening our understanding of the TOV limit, the neutron equation of state, and the origins of the heavy elements. With every detection, the boundaries of theory bend closer to the truth. The gold of the dead, it's humbling to realize that the most precious materials in human civilization come from the wreckage of cosmic violence. Every gram of gold on Earth was once trapped inside a neutron star, compressed in the gravity of a dead sun, then hurled across space by an explosion that warped the universe itself. The metal that crowns kings, fills vaults, and forms wedding rings is, in truth, the ash of destruction. It is the residue of collapse, the light of death made tangible. The rings we cannot hear. If we could translate the gravitational waves of neutron star mergers into sound, they would form a rising tone, a chirp that climbs in pitch as the stars spiral together. At first, it would be a deep hum, inaudible. Then, as the orbit shrinks, it would rise, faster, higher, until it reaches a crescendo and abruptly cuts off. That final note, the last vibration before silence, marks the moment of merger, the instant when 2 stars become one. Somewhere, right now, that sound is happening. A ripple in spacetime is racing through the galaxy, carrying news of another collision, another birth, another end. And perhaps, in a few years, our detectors will hear it, another whisper from the dark. The universe as composer. When the gravitational wave data from GW 170817 was first converted into audio, it lasted less than 2 seconds. Yet that tiny sound contained the story of 2 stars, billions of years old, colliding to create everything from gold to platinum. It was the faintest, most beautiful sound ever recorded, the sound of the universe playing its own music. For the first time, we weren't just observers of that cosmic symphony. We were participants. The stars that die so we can exist, the atoms in your bones, calcium, iron, and phosphorus, were forged in the cores of long-dead stars. The gold in your blood, the iodine in your brain, the silver in your veins, those came from neutron star collisions. The universe's violence built us. Every breath we take is made possible by explosions we can barely comprehend. When we study kilonovae, we are not merely studying the death of stars. We are tracing our ancestry, the cosmic genealogy of matter itself. The next time you hold a piece of gold, remember this: you are touching the relic of a collision so powerful it made the universe ring. And though the sound has faded across millions of light years, the echo remains in you. Part 9, Gravitational Waves and the Map of Reality. How we learned to hear the universe. For most of human history, astronomy was an art of sight. We looked at the sky, not listened to it. Our ancestors charted constellations, watched comets blaze, and tracked the motions of planets, all through light, reflected, emitted, and refracted. But light can only tell part of the story, can be blocked by dust, bent by gravity, or lost in distance. For centuries, the universe seemed silent. Then, in the 21st century, humanity built something new, a way not to see the cosmos, but to hear it. And with that first whisper from the dark, reality itself gained a new dimension. The impossible machine in the high desert of Hanford, Washington, and in the wetlands of Livingston, Louisiana, two structures stretch across the land like metallic arrows, each arm 4 kilometers long, perfectly straight, shining under the sun. This is LIGO, the Laser Interferometer Gravitational Wave Observatory. At first glance, it looks like nothing more than a pair of empty tunnels. But inside those tunnels, beams of laser light travel back and forth, reflected by mirrors so precise that even the vibration of a passing truck could disrupt them. When a gravitational wave passes through Earth, it stretches one arm of LIGO while compressing the other by less than 1/10,000th the width of a proton. The lasers detect that tiny difference, turning the distortion of spacetime into data. It is, quite literally, an instrument that measures the heartbeat of the universe. The idea of such a machine was once considered absurd. In the 1960s, when physicist Joseph Weber first tried to detect gravitational waves using aluminum bars, many of his peers doubted that such signals could ever be measured. The distortions were too faint, the noise too great. But physicists like Rainer Weiss, Kip Thorne, and Barry Barish refused to give up. They spent decades refining the design, isolating vibration, perfecting lasers, and training generations of scientists to read silence. Their perseverance paid off. The first sound of space on September 14, 2015, the universe made its first audible entrance. At 9:50 and 45 seconds Universal Time Coordinated, both LIGO detectors picked up a faint, rising tone, a chirp lasting just 0.2 of a second. It came from the merger of two black holes, each over 30 times the mass of the Sun, colliding more than 1 billion light-years away. The signal was dubbed GW 150914. When the data was converted into sound, it was eerily simple, a low whoop that rose in pitch and stopped abruptly. That was it. Two black holes, invisible and silent in light, had announced their union by vibrating the fabric of reality itself. Einstein had predicted this moment a century earlier, yet doubted it could ever be measured. Now it was undeniable. For their achievement, Weiss, Thorne, and Barish received the 2017 Nobel Prize in Physics. But more importantly, the world had gained a new sense. Humanity could now hear gravity. A symphony expands within 2 years. LIGO had a partner, Virgo, a European observatory near Pisa, Italy. Together, the three detectors formed a global network capable of triangulating the sources of gravitational waves, pinpointing their locations across the sky. In 2020, Kagra, a Japanese detector buried deep beneath the mountains of Gifu Prefecture, joined the collaboration. Unlike its predecessors, Kagra's mirrors were cooled to near absolute zero, reducing noise to unprecedented levels. Soon, another generation of instruments will rise. The Einstein telescope in Europe and LISA, the Laser Interferometer Space Antenna, a constellation of satellites that will orbit the Sun, forming a detector millions of kilometers wide. With these machines, we will no longer be confined to hearing the loudest events. We'll hear the background hum of the entire universe, a gravitational symphony that's been playing since time began. The universe in stereo, each detection tells a story. Black hole mergers give us the rhythm of gravity. Neutron-star collisions give us harmony, the combination of gravitational waves and light. By comparing these signals, astronomers can now map the universe in a completely new way. In traditional astronomy, distances are measured through light, by brightness, redshift, or spectral analysis. But gravitational waves offer something purer: standard sirens. Just as standard candles like Type Ia supernovae help us gauge cosmic distances through luminosity, standard sirens let us do the same using sound. By measuring the amplitude and frequency of a gravitational wave, scientists can calculate precisely how far away its source is, independent of any assumptions about light or dust. For the first time, we can measure the expansion rate of the universe, the Hubble constant, using gravity alone. And intriguingly, these measurements don't quite agree with those made using light. The two values differ by several percent, a tension that may hint at something profound. Perhaps the laws governing cosmic expansion are changing, or perhaps dark energy, the mysterious force driving the universe's acceleration, behaves differently than we thought. Gravitational wave astronomy isn't just confirming our theories, it's rewriting them. The quiet revolution each year, the number of gravitational wave detections grows. At first, they came as rare miracles, 1 or 2 per year. Now, LIGO and Virgo record dozens. Soon, with upgrades, they may capture hundreds. Every event adds another note to the cosmic score. Binary black holes colliding in distant galaxies. Neutron stars merging in brilliant kilonovae. Even black hole-neutron star pairs, rare unions of light and darkness. Together, they form a pattern, a living map of spacetime. And that map isn't flat. It ripples, flexes, and hums with motion, revealing that the universe is far from quiet. It is alive with vibration. The cartographers of the void, there's something poetic about the fact that the universe, once thought to be silent, turns out to sing. Each gravitational wave detector is like an ear pressed to the cosmos, listening for whispers from its farthest corners. And the people who operate them, scientists, engineers, programmers, are modern cartographers, mapping an ocean not of space, but of time itself. They sit in control rooms surrounded by silence, watching screens flicker with noise. Most of the time, the data shows nothing but static. But occasionally, for a fraction of a second, the line trembles. A chirp appears, and everyone in the room knows what it means. Somewhere, billions of light-years away, two colossal bodies have collided, and the universe has just told us about it. That moment, that instant of recognition, is as close as science gets to religion. Seeing without light, the great power of gravitational wave astronomy is that it allows us to see what light cannot. Black holes, for instance, emit no light. They are defined by darkness. Yet when two black holes merge, their gravitational ripples can travel across the cosmos unimpeded. Through those ripples, we can study objects otherwise invisible, probing not their surfaces, but the geometry of the spacetime they distort. For the first time, we can map gravity itself. In the future, as detectors grow more sensitive, we may even detect the faint, primordial gravitational waves left over from the Big Bang, the original echo of creation. If that happens, it would be the ultimate map, a picture not of stars or galaxies, but of the birth of the universe itself. The sound of everything. When you step back and listen to what gravitational wave astronomy represents, it becomes clear that it's more than a technical triumph. It's a new way of experiencing reality. We used to think of the cosmos as a painting, silent, luminous, and distant. Now we know it's a symphony, and we are part of its orchestra. Every second, space around you is being stretched and squeezed by waves from ancient collisions. You can't feel them, but they pass through your body, through mountains and oceans, through the earth itself, the breath of creation continuing everywhere, always. The universe has been singing since the beginning. We just finally learned to listen. Part 10. The Magnetic Titans. Magnetars, starquakes, and the limits of power. There are stars that shine, stars that pulse, and stars that collapse. But among the ashes of stellar death, there exists another kind. A monster wrapped in magnetism, where the laws of physics twist like iron under strain. These are magnetars, the most magnetic objects in the known universe. If neutron stars are the densest matter we can see, magnetars are its most volatile incarnation. Stars so charged with magnetic energy that their very surfaces quake and crack like glass under stress, releasing bursts of power that can rival the energy of the sun emitted over 100,000 years. They are the titans of the magnetic cosmos, the restless corpses of once massive suns. The birth of a monster magnetars are born in violence, the aftermath of supernovae that collapse under their own weight, compressing mass into a city-sized sphere. But for reasons still not fully understood, a small fraction of these neutron stars form with extreme magnetic fields, trillions of times stronger than anything found elsewhere. A typical neutron star's magnetic field measures around 10 superscript 1 superscript 2 Gauss. A magnetar's can exceed 10 superscript 1 Gauss. To imagine that strength, consider this. If a magnetar were placed halfway between Earth and the Moon, its magnetic pull could erase every credit card and hard drive on Earth. At a distance of 1,000 kilometers, it would distort the electrons in your atoms, tearing molecules apart. Such power cannot exist quietly. Within milliseconds of birth, the newborn magnetar spins hundreds of times per second. Its rapid rotation and magnetic field amplify each other in a feedback loop, converting rotational energy into magnetic fury. The result is a star whose magnetic stress deforms even the solid crust of neutron matter. It is, in every sense, a ticking bomb. The crust that cracks a magnetar's crust is only a few kilometers thick, a shell of neutron-rich nuclei embedded in a sea of degenerate electrons. It is one of the strongest materials in the universe, but even it has limits. As the magnetic field twists and realigns deep below the surface, the crust strains under pressure. Eventually, it snaps. This sudden rupture releases a torrent of electromagnetic energy, an X-ray flare or, in the most violent cases, a gamma-ray burst. These starquakes are the cosmic equivalent of earthquakes, but unimaginably larger in scale. The energy released in a single event can equal that of all the world's nuclear weapons detonated simultaneously, multiplied by 1 billion. When the magnetar SGR 1806-20 erupted in December 2004, the flash of gamma rays briefly outshone every other source in the Milky Way. Even after traveling 50,000 light-years, it was strong enough to ionize Earth's upper atmosphere. Had it been only 10 light-years away, it might have stripped our planet's ozone layer clean. Astronomers recorded the pulse, watched the magnetar fade, and then listened as its magnetic field began to twist again, recharging for the next eruption. The fire that spins magnetars are not steady emitters. They flicker, pulse, and occasionally fall silent. When active, they unleash soft gamma repeater SGR bursts, sequences of flashes lasting fractions of a second to several minutes. Each burst rearranges the star's outer layers, changing its spin slightly. The result is a measurable glitch, a sudden acceleration or deceleration in rotation. To observers on Earth, these changes look like irregularities in a cosmic metronome. But what they reveal is astonishing. Even after death, these stars move. Their magnetic fields flow like rivers of iron. Their crusts grind and shatter. Their interiors boil with plasma. Every pulse we detect from a magnetar is a message written in tension. Gravity trying to crush, magnetism trying to twist, quantum mechanics trying to hold them apart. The outcome is not peace, but balance through violence. The pulse that shook a galaxy in April 2020, a magnetar named SGR 1935+2154, located about 30,000 light-years away, did something extraordinary. It emitted a millisecond-long burst of radio waves so powerful it was detected across multiple observatories on Earth. For decades, astronomers had been puzzled by fast radio bursts, FRBs, mysterious, ultra-bright radio pulses coming from distant galaxies. They appeared without warning, lasting only thousandths of a second, each releasing more energy than the sun emits in a week. The source of FRBs was a cosmic mystery. Some speculated black holes, others alien civilizations. But SGR 1935+2154 changed everything. Its radio outburst was almost identical to an FRB, only weaker because it came from inside our own galaxy. For the first time, scientists had direct evidence that at least some FRBs come from magnetars. The implication was profound. Across the universe, billions of these magnetic corpses may be flashing like beacons, sending brief, brilliant pulses through the cosmic dark. Each one is a reminder that even the dead can still shout. The geometry of fury, the magnetic field of a magnetar, isn't static. It twists, buckles, and reconnects, like the tangled loops of a storm's lightning. When these field lines snap and rejoin, they release vast amounts of stored energy, similar to solar flares on the sun, but magnified by a trillion. Inside the magnetar, those magnetic stresses penetrate all the way down to the core, where neutrons may exist as a superfluid. Some models suggest that these internal fields can actually distort the star's shape, turning it from a perfect sphere into an elongated ellipsoid. Such distortions can cause the magnetar to wobble, emitting gravitational waves of its own. Faint ripples that could, in the near future, be detectable by advanced observatories like LIGO A+ or the Einstein telescope. If we can detect those waves, we would be hearing not a collision, but a heartbeat, the living vibration of a single star in magnetic agony. The light that burns two bright magnetars burn out quickly. Their magnetic fields decay over tens of thousands of years, a blink in cosmic time. As they fade, their violent outbursts cease, their spin slows, and they become indistinguishable from ordinary neutron stars. But while they live, they shape galaxies. Their eruptions inject energy into interstellar space, triggering new waves of star formation. Their magnetic winds sculpt nebulae, leaving twisted tendrils of gas and plasma that can stretch for light years. And their explosions, when they finally collapse into black holes, may be responsible for some of the short gamma-ray bursts that flicker at the edges of the observable universe. The irony is exquisite. The stars that die most violently are also those that give birth most prolifically. When power meets fragility, to study magnetars is to confront the paradox of existence itself. They are both fragile and indestructible, balanced between annihilation and endurance. Their crusts crack like glass, yet their cores endure more pressure than atoms can imagine. The same quantum rules that govern the orbits of electrons in your body also dictate how their remnants behave under a trillion Teslas of magnetic force. Physics doesn't change. It simply scales to the unimaginable. We, too, are part of that same rulebook, products of the same tension between structure and collapse. If a magnetar could feel, perhaps it would know what it means to live under pressure, to hold form in the face of impossible stress. The universe's nerves. Some scientists describe magnetars as the nervous system of the galaxy. Sudden jolts that remind us the cosmos isn't static. Each burst is a synapse firing across millions of light years, a twitch in the body of the universe. They are proof that even in death, stars can still influence the living. They reshape space, ignite new stars, and send whispers across the void. The universe's heart may be dark, but its nerves still spark. Part 11. The Dark Collapse. When neutron stars become black holes, every limit has a moment when it yields. Every fortress has a wall that eventually cracks. And in the universe, even the densest star, even the defiance of quantum pressure itself, must someday bow to gravity. When that moment comes, the neutron star story ends. But what follows is not silence. It is transformation. The star does not explode. It folds. The space it occupies bends inward. The fabric of reality itself begins to curve, deeper and deeper, until there is no surface, no boundary, no escape. This is the birth of a black hole, the final surrender of matter to its own gravity. The moment of no return, and neutron star stability depends on its internal pressure, the quantum degeneracy of neutrons resisting compression. But there comes a point, defined by the Tolman-Oppenheimer-Volkoff limit, where that pressure can no longer hold. Once the star's mass exceeds roughly 2.3 solar masses, the inward pull of gravity overwhelms every known force. The collapse happens in microseconds. The crust fractures, releasing one last flash of X-rays. The neutrons themselves disintegrate into a sea of quarks and gluons, but even that state cannot resist. Space-time caves inward, the escape velocity surpasses the speed of light, and a horizon forms, an invisible boundary beyond which nothing, not even information, can return. To an outside observer, the collapse seems to freeze in time. The star's surface slows, redshifts, and fades as light from it takes longer and longer to reach us. But from the star's own frame of reference, the fall continues inexorably. There is no impact, no floor, no final crash. The the star simply becomes smaller than space itself. The birth of the horizon, the black hole, begins not as an object, but as a region. Its defining feature, the event horizon, is the boundary between what can be seen and what cannot. Inside that horizon, gravity is so strong that all paths curve inward. Outside it, the universe remains untouched. From a distance, the newborn black hole appears as a sphere of darkness surrounded by the faint afterglow of its own formation. A photon ring, created by light orbiting at the edge of the abyss. No light escapes, yet paradoxically, the region around the black hole shines more brightly than almost any other in the universe. Gas and dust caught in its gravity spiral inward, heating to millions of degrees before crossing the horizon. The resulting accretion disk emits powerful X-rays and gamma rays, visible across galaxies. Thus, the object born of darkness becomes one of the brightest beacons in the sky. The echo of collapse: if a neutron star collapses after a merger, as in the aftermath of the kilonova GW 170817, the transition is marked by a sudden change in gravitational wave signal. Physicists call this the ring-down phase. For a fraction of a second after the horizon forms, space-time itself vibrates like a struck bell. The frequencies of those vibrations, the so-called quasi-normal modes, depend on the mass and spin of the new black hole. By listening to those vibrations, scientists can test one of the deepest predictions of general relativity. The no-hair theorem, which states that black holes are completely defined by just three quantities: mass, charge, and spin. If the vibrations ever deviate from those predictions, it would mean that something survives inside, that perhaps the collapse leaves behind more than the equations allow. No deviation has been found yet, but every new detection is another chance to ask, is the void truly empty? The event horizon as mirror: it's tempting to think of a black hole as a cosmic drain, a place where things go to die. But in truth, it is more like a mirror that hides what it reflects. Everything that falls in light, dust, stars, even neutron matter, adds to the black hole's mass and spin. Yet, information seems to vanish, and that disappearance poses one of the greatest paradoxes in modern physics: the information problem. According to quantum mechanics, information cannot be destroyed. According to general relativity, anything crossing the event horizon is lost forever. Both cannot be true. This contradiction, the clash between gravity and quantum theory, has haunted physics for half a century. Some scientists, like Stephen Hawking, propose that black holes aren't completely black. Quantum fluctuations at the event horizon cause them to emit faint thermal radiation, now known as Hawking radiation. Over time, that radiation can cause a black hole to lose mass and eventually evaporate. If that's true, then perhaps information isn't destroyed but encoded, hidden in the quantum structure of the horizon itself, slowly released over billions of years. The neutron star, in dying, may have become the most perfect storage device in the universe. When neutrons meet nothingness inside the event horizon, space-time no longer behaves in any way that words like inside or distance can describe. Relativity predicts that all paths lead to a singularity, a point of infinite density where our equations collapse. But physicists suspect this singularity is a sign of our ignorance, not infinity itself. Perhaps, deep within, the quarks and gluons of the former neutron star transition into an entirely new state of matter, one that bridges quantum mechanics and gravity. Some call it the Planck core, a region of quantized spacetime. Others imagine a bounce, where matter falls inward, compresses, and then expands into another universe, a cosmic recycling that turns black holes into the seeds of creation. The idea is speculative, but poetic, that every collapse births a new beginning, every end becomes a womb. The ghost of the star, even after its surface disappears, the legacy of the neutron star remains written in its spin and magnetic field. A rapidly rotating neutron star collapsing into a black hole can drag those fields along, twisting them into immense jets of plasma that shoot out perpendicular to the disk. These relativistic jets can stretch for thousands of light years, carrying energy equivalent to billions of supernovae. When we observe distant quasars or blazars, bright, flickering points powered by supermassive black holes, we are seeing this same process on a cosmic scale. Every black hole, in a sense, carries the ghost of the star that birthed it. Its angular momentum, its magnetism, its final spin, preserved in geometry. Even in disappearance, the neutron star leaves a trace. The light that falls and the light that stays from Earth. The death of a neutron star is invisible. No telescope can see through the horizon. And yet, the story is not hidden. The gravitational waves from the collapse, the fading afterglow of its accretion, the slowing pulse of its magnetic field, these are echoes we can still measure. Through them, we reconstruct the moment of transformation. When matter stops being matter. When time ceases to flow as we understand it. When the universe swallows one of its own creations and, in doing so, rewrites itself. The black hole is not destruction. It is containment, the universe preserving its contradictions within silence. The line between being and nothing, the neutron stars fall into darkness, is more than a physical event. It is a philosophical boundary, the point where knowledge itself ends. We cannot peer beyond the horizon, yet we cannot stop imagining what lies there. It is the edge of science and the beginning of myth, and perhaps that is fitting. Because if the universe has a soul, it is not in the light that shines, but in the darkness that endures. For there, in the quiet beyond all forces, the last heartbeat of matter becomes the first whisper of eternity. Part 12, The Universal Equation. What neutron stars teach us about everything. The story began with light, the first fire of the cosmos, the birth of stars, the ignition of atoms. But as we reach the end, we find ourselves not in brilliance, but in darkness. Not in expansion, but in collapse. And yet, that darkness is not an ending. It is the place where understanding begins again. Because in the death of stars, in their implosions, their pulses, their silent vanishing, the universe has revealed its deepest code. A set of principles that govern not just matter and gravity, but meaning itself. The equation of existence in the heart of every neutron star. Three fundamental forces are locked in combat. Gravity, the inexorable pull inward. Quantum pressure, the resistance of matter to being compressed. The strong nuclear force, the glue holding quarks together. Their balance is the same balance that shapes everything, from the orbit of planets to the stability of atoms, from the curvature of galaxies to the architecture of DNA. What happens inside a neutron star is the universe reduced to its purest confrontation. The will to collapse versus the will to endure. That struggle produces not chaos, but structure. Not destruction, but renewal. Every time a star dies, it distills complexity into simplicity, and in that simplicity, we find the blueprint for everything that comes after. We are made of those blueprints. The carbon in our cells, the calcium in our bones, the iron in our blood. All were once the debris of collapse. You are not made of starlight. You are made of resistance, of the brief, furious defiance of matter before it yields. The universe as a self-measuring machine, every star that forms, burns, and dies is an experiment. A self-running equation testing the limits of its own laws. Neutron stars push matter to densities where the familiar dissolves. Black holes stretch time until it folds. Gravitational waves translate the violence of these deaths into music, vibrations that reveal the shape of space itself. Through them, the universe is doing something extraordinary. It is measuring itself. When two neutron stars collide, they broadcast not just energy but information about mass, spin, density, and the nature of spacetime. Those signals ripple outward, cross billions of light years, and arrive at our small planet as faint tremors in our detectors. And when we decode them, we close the loop. The universe observes itself through us. We are its sensory organ, the part of existence that has become aware enough to turn the cosmos into data, and data into understanding. Matter's last defense inside a neutron star, the battle between gravity and quantum pressure, is more than a physical process. It's an existential metaphor. Gravity says, collapse. Quantum mechanics says, not yet. That tension, the refusal of matter to vanish, is the reason anything exists at all. If the strong force were slightly weaker, atomic nuclei would disintegrate. If gravity were slightly stronger, the first stars would have collapsed before they could shine. If quantum rules were different, matter itself would not have form. The universe balances on a knife's edge of fine-tuned parameters, and neutron stars sit exactly at that edge. They are not anomalies. They are evidence that reality itself is a compromise, a negotiated truce between symmetry and entropy, between energy and order. The map hidden in collapse from the outside, neutron stars are opaque. No telescope can see beneath their crusts. But their existence traces the outlines of an invisible landscape, a map of matter from the familiar to the unimaginable. Atoms, held by electromagnetism. White dwarfs, held by electron degeneracy. Neutron stars, held by neutron pressure. Quark stars or strange stars, perhaps held by the strong force alone. And beyond them, black holes where even force loses meaning. This progression is not just a hierarchy of density. It is a gradient of comprehension, a descent into the places where our mathematics falters. Each step deeper demands a new equation of state, a new vocabulary of being. And somewhere between neutrons and nothingness, we will finally learn how to merge gravity with quantum mechanics, the dream of Einstein and the unfinished promise of 20th century physics. When that happens, the first place we'll test it will not be in a lab, but in the light of a dying star. Time, reversal, and the eternal loop. A neutron star is a clock that keeps time for the universe. Its spin, precise to billionths of a second, serves as a cosmic metronome. But as it emits energy, through radiation, magnetic storms, or gravitational waves, its rotation slows. Eventually, it fades into stillness. And yet, in that decay lies the seed of renewal. The matter ejected in its birth, the gold and platinum born in its collisions, drift through interstellar space until they find new clouds to enrich, new stars to ignite. In time, those new stars will die and leave behind new neutron stars. Collapse leads to creation. Creation leads to collapse. The universe is not a linear story but a loop of transformation. Energy folding into matter, matter into light, light back into space. The end and the beginning are the same equation, written backward and forward. The human constant somewhere along that cosmic cycle, consciousness appeared. It's easy to see ourselves as insignificant, small creatures on a pale planet, adrift in infinite black. But perspective matters. In the life of the universe, there have been countless collapses, countless deaths, but only one kind of event has ever looked back at them and asked why. That event is us. We are built from the same particles that fought gravity inside those stars, and yet those particles have learned to name themselves, to simulate their own collapse in equations, to imagine their own end. The universe dreamed of awareness, and it became us. When we listen to gravitational waves, when we chart the lives of neutron stars, when we speak of quarks and horizons, we are hearing the echo of our own substance remembering itself. The equation without an equal sign in school. Equations are tidy. Left side equals right side. But the universe's equation doesn't balance, it flows. On one side is order, the formation of atoms, stars, and life. On the other is entropy, decay, collapse, black holes. Between them is the motion that keeps both alive, transformation. Neutron stars are the perfect symbol of that motion. They are order compressed to the brink of chaos, harmony held together by contradiction. If you could write the universe as a single formula, it would not be E equals mc squared. It would be resistance plus collapse equals existence. That's what neutron stars teach us. That everything, from galaxies to consciousness, survives only because it refuses to stop falling. The universe's self-portraits stand outside on a clear night. Every point of light you see is a note in the cosmic score, every flicker the echo of forces that shaped your body and mind. Somewhere, perhaps right now, two neutron stars are merging, their gravitational waves already en route to Earth. In a few 100 million years, that wave will pass through you, a silent ripple in the space between your atoms, carrying the memory of a son's death. You won't feel it, but it will happen. And in that instant, the circle will close again. The dead stars whisper, and the living stars, us, listen. The final lesson: if the universe has a message written into its structure, neutron stars are the punctuation marks. Dense, precise, absolute. They remind us that the laws we study are not cold abstractions but living processes. That pressure, failure, and collapse are not endings but evolutions. That light comes not despite gravity, but because of it. The cosmos is not a hierarchy of things, but a conversation of forces, a tension that produces meaning. And meaning, like gravity, bends everything toward it. So when a neutron star dies, when it crosses the horizon and disappears, it does not end the story. It becomes the next sentence. The universe keeps writing. Epilogue: the star within the atoms that once resisted collapse now live as thought. You are a continuation of that resistance, a fragment of the cosmos trying to understand itself. Perhaps that is the real equation of everything. The universe becomes conscious the moment it begins to wonder where it came from. And as long as there are eyes that look up, instruments that listen, and minds that ask why, the stars, even the dead ones, will never truly fade.